Hey! Hello there. I must say, I am pretty impressed with how you guys are doing with logs. You know, I know most of them can be done right in the calculator, but you guys are really embracing it and trying to learn it. Algebra 2, you can do most of the work on your calculator, and the exam doesn't know whether or not you know how to do it. So if it's a part 1 question, of course you use your calculator. But like I said, I'm very impressed with how you guys are learning how to use the logs, and some of you realize that they're really not that bad. Okay, once you find out exactly what the premise is and what you need to do. Now, there's another type of log that they use, and we're going to use in calculus when you get to the higher level math here, and it deals with the letter E, which is actually a number. So it's like pi. You know, pi is 3.14. E is approximately 2.72. So they use the E as what we're going to be calling a natural log. Now, if you look at this exercise here, which of the graph below shows y equals e to the x. And if it's a part 1, if you see something like this in a part 1 question, of course you could just put in your calculator. But we just said that e is 2.72. So when we looked at a previous unit, this is unit 4, lesson 12. When we saw in a previous lesson that when we put in our calculator and it was greater than 1, it was an increasing function like this one. Okay, clearly it's not 1 or 4, so your only choice should have been 2 or 3. And if you put it right in your calculator, it would have worked. Okay, so like I said, the explanation, because e is greater than 1, must be the increasing exponential graph. And yes, e is used in growth and decay. There are formulas that we will use that we will see e in the formula. Some are given to you, some we will have to remember and apply. We're talking about compounding interest. So the population of llamas on a tropical island can be modeled by the equation P equals 500e raised to the 0.035 t. T represents the number of years since llamas were first introduced to the island. So how many llamas were initially introduced? So at t is 0. So this is your 500. Okay? And if you were to put 0 in, of course, for t, that's going to make this whole part 1. And then you multiply that by 500, and that's why you get 500. Okay? And that's your starting point. So the second one says, algebraically determine the number of years for the population to reach 600. So you should have enough room to do this. So if I want the population to be 600, I have 600 equals 500 e to the 0.035 t. So remember, when you have a variable in the exponent, you have to get the term with the variable in the exponent by itself. So what is being raised to this 0.035 t? Just the e, not the 500. So you got to divide both sides by 500. Now, you know the old trick, if you have the zeros, they can just cancel out. So it really just becomes 6/5. Okay? Now, just leave it as 6/5. That's fine. Some of you guys are putting in the calculator, and if it's a terminating decimal, no big deal. But if it's a non-terminating decimal, you don't know where to stop. So you just leave it as a fraction. Makes it easier. Okay, so there's your new equation. Now remember, we're going to log it. So what we've learned so far is we just do a log. Okay, 6/5. And I'm going to do this because some of you guys are at this point. Okay, because when you do the log of both sides with the power rule, it's going to come down out in front. Okay, so then we have this. And what do? We can divide. We can do it all at once. 0.035 log e. 0.035 log e. Okay? So we're going to go to the calculator. And this is where it gets a little tricky. Be very careful. So we have, whoop, I don't want to do that. Why'd that happen? So it's a control, okay, with your division. So here's your log. And we don't want the base because the base is just your base 10. Control, and that was 6/5 I had. And then that's divided by log of E, okay? Base 10 again, and there's your E right there. Okay, you can just put 1 if you want. Okay, so remember, it's the E up here on the keys, not the letter E down here. Okay, can you see where I'm moving my arrow? Okay, so then we have that. Oh, but I forgot to put in front of the log the 0.035, and I might need a time symbol there. And enter, and you get 5.2. Okay, it says the nearest tenth of a year, so that would be just 5.2 years. Don't do 5.21 because that's the 100th. Okay, so we have y equals e to the x. Okay, its inverse would be throwing the log in, so it would be this guy right here. That would be its inverse. Y equals log base e to the x, which we've already gone over in a previous lesson. Now, log base e is a natural log, which is ln. So ln means a natural log, means log base e. Okay, so that button on your calculator is to, if you can see my cursor again, there's your log, right? Second log. If I do control e to the x, boom, there's your ln. Okay? So without using your calculator, well, of course, you'll always be able to put it in. So if you wanted to put it in, here we go. I'll show you how to put it in. So there's your natural log, and then you just have e, and if I just hit enter, okay, I got to put something there. I couldn't remember if I had to or not. So you just put a 1 there, and enter, and it gives you 1. And I'll show you why that's true. Because of what we did previously. Remember, if we change this and we say, okay, let it equal x. So ln is, remember, log base e equals x. So remember, we had the e to the x equals e to the 1. Bases are the same, x equals 1 like we just showed. Okay? If this right here equals x, again, log e of 1 equals x. E to the x equals 1, x equals 0. Okay? This equals x. Log e to the 5 equals x. E to the x equals e to the 5. X is 5. Okay? This one here, I'm not going to show you the e again. This equals x. E to the x equals square root of e. E to the x equals e to the 1/2. X is 1/2. Okay? Done. So again, you'll always have the use of your calculator, but that's the premise where it comes from. Okay? And as you use logs more and more often, you will become familiar with it. Now, the natural log follows the same basic law logs that all logarithms follow. So if we have division, it goes with subtraction. Multiplication goes with addition. Power rule, same thing comes down in front. Okay? So with this here, exercise 4, if I was to evaluate this, this would be ln x cubed minus ln e squared. So 3 ln x minus 2 ln e. Okay? Now ln e, which we already did in example 1, ln e equals 1. Okay? So this is 1. So that means I have 3 ln x minus 2. And that is choice number 2. Okay? Now, exercise 5. What's going to happen in the regions 2 is they're going to give you a formula that you may have never seen before, and then you just have to apply it based upon what is given. So the hot liquid is cooling in a room whose temperature is constant. Its temperature can be modeled using the exponential function below. Temperature T is degrees Fahrenheit. And a function of the number of minutes m, it has been cooling. What is the initial temperature of water at m equals 0? So m equals 0, I plug it in right there. M equals 0, that is gone because it becomes 1. Okay? So then I have 100 plus 67 is 168. Okay, so that was the initial temperature. All right? And then, how do you interpret the statement that T60 equals 83.7? Well, 60 goes in for M. M is minutes. So after 60 minutes, or 1 hour, The temperature is 83.7 degrees Fahrenheit. So if you want to write that down, write it down. Okay? Using the natural logarithm, determine algebraically when the temperature liquid will reach 100 degrees. Okay? So we want it to be 100 degrees. It started at what? 168. So we have 100 equals. 100 equals, and I got to look at the formula here. 101 E negative 0.03 M plus 67. All right, so follow your order of operations here, your inverses. Minus 67, minus 67. Okay, so I have 33 equals 101 E to the negative 0.03 M. Divide by 101, divide by 101. So this is what I'm talking about, where it's an ugly number. Okay, so it's gone over here. So we have 33 over 101 equals E to the negative 0.03 M. Now you see that variable as the exponent. I know you're chomping at the bit to throw a log in front of it. Now, what we're going to do, because of this base E, it would work out the same if you use log or if you use what I'm going to show you now. So instead of using log, because the base is E, we're going to use the natural log, which is the ln. So ln E to the negative 0.03 M. Okay? So that way we have natural log of 33 over 101 equals negative 0.03 M ln E. Okay? So ln of E is 1, so it's gone. That's why we use the natural log. So then we just have to divide this by negative 0.03. Divide this by negative 0.03. Okay? So I'll show you how this is done in your calculator. So we have our fractions. Here's your ln button. Control E to the x. There's ln. Control fraction. 33. So now if we use the accurate fraction, you don't have to worry about rounding or how far do you round it. So use the fraction for accuracy. And I think that's right. Yep, that's good. Enter, and we have 37 point, and it says tenth of a minute, 37.3. Okay, so we have 37.3. Okay, so that's how you solve for that one. Now, on average, how many degrees are lost per minute over the interval? 10 to 30, round to the nearest tenth of a degree. Okay, so we want between 10 and 30, so we need to find the output at 10 and 30. Where am I going? I'm going here. Okay, so I'm going to pause it. I was going to pause it, but I want to show you where the E to the X. So you have 101, and I think that's what it times, E to the X. So there's your E to the power, negative 0.03, and I'm just using X again, okay, instead of M, and then I'm getting out of there, plus 67, control such that, okay, such that X equals 10. Enter. 141.823. Bring this down. I need 30. Delete, delete. Oh, I didn't do that. Delete to 30. There's your output, 108. Okay, 0.1. I'm going to go to the 10th. Actually, I'm not going to go to the 10th because it says round to the nearest 10th at the end. Okay, so 141.823, 108.064. Okay, now here we go back to this. All right, so loss per average rate of change. Okay, 10 comma 141.823, 30 comma 108.064. I want you to find the average rate of change of those two numbers. Okay, 2 points, I'm sorry, of those two coordinates, and that's what I am going to be collecting tomorrow in class. Okay. Oh, do I have time for the song? All right, we're going to end on it. Okay. We'll see you in class.